The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Hi, I'm Jocelyn, and today we're going to go over the exam 2 from fall 2009 and problem 4, parts A and B. As always, we're going to start by reading the question. Boron exists in the gas state as the dimer boron 2. Explain how the fact that B2 is paramagnetic, 2 unpaired electrons, implies that in this molecule the pi 2p orbitals must lie at a lower energy than do the sigma 2p. Okay, so what is this question actually asking you to do? Well, it's asking you why the energy of the pi 2p is less than the energy of the sigma 2p, given that boron 2 is paramagnetic. So the first thing we need to know is what paramagnetic means, and he actually gives that to you in the problem. So it means that you have 2 unpaired electrons. So this is unpaired electrons. We are asked here then to give a reason why the fact that there are unpaired electrons implies a certain ordering of the sigma and pi 2p orbitals. So the first thing we want to do probably is recognize that these are molecular orbitals, not atomic orbitals. Therefore, we probably want to start by drawing the molecular orbital diagram for boron. Now, how do we draw a molecular orbital diagram? Well, the first thing to do is to start with the atomic orbitals. So boron has 5 electrons, as we can find out from our periodic table. And they occupy the 2s, 2s, the 1s, the 2s, and 1 electron in the 2p. Again, if this seems unfamiliar to you, you might want to go back to earlier in the course where we went over electron configuration. However, when we're looking at molecular orbitals, we actually only care about the valence electrons because those are what are involved in bonding. The core electrons are much, much lower in energy, so they aren't really involved in the bonding. So we're actually only going to look at the electrons in the second energy level. So we have 3 valence electrons per boron. And they are in the 2s and 2p, which we remember there are 3 p orbitals in each energy level. So now let's draw those in. We have 2s and 2p. Remember to always have a scale here, and we're in an energy space. And this is not to scale, because we're just looking at relative energies. We don't care about the actual difference in energy. And because we have 2 borons, so this is boron 1, I'm going to draw the same thing over here. Make sure they're at the same energy level because they are the exact same atom and therefore the same atomic orbitals. So this is, again, boron. And we have 3 electrons for each. We don't have to fill them in, but I'm going to do so just to keep track. And again, we're filling according to the orbital filling rules gone over earlier in the class. So now that we have our atomic orbitals, we are going to combine them to molecular orbitals. And we want to remember that s orbitals combine to make a sigma and a sigma bonding and a sigma antibonding. Remember that whenever you combine atomic orbitals, you create, if you're combining two atomic orbitals, you create one of a higher energy and one of a lower energy, because the net energy stays the same. Oh, sorry, that's crooked. All right. Now we'll move on to the 2p. And because the problem told us that we need to explain why the pi bonding orbitals are lower in energy than the sigma bonding orbitals, we're going to start with that configuration. The actual order depends on the molecule, and so without any extra information, we wouldn't really know if the sigma was above or below the pi. So as the question kind of hints at, p orbitals make 2 pi bonds and 1 sigma bond. This is due to the orientation of the pi bonds or the p orbitals in space. And then, as always, we need to put in the antibonding. Just to make sure we keep track of all of our orbitals. Okay, so we combined 1, 2, 3, 4, 5, 6, 7, 8 atomic orbitals, and we made 1, 2, 3, 4, 5, 6, 7, 8 molecular orbitals. We want to make sure we always have the same number of orbitals before and after. So now we can fill in the electrons into the molecular orbitals. That's these in the middle here. And we use the same rules as we do when we're filling atomic orbitals. So we start at the lowest energy, pairing spins if we only have one orbital in the energy level. But as here we have degenerate orbitals, so we can actually have unpaired spins. So we have 1, 2, 3, 4, 5, 6 electrons, and we had 3 from each boron molecule atom, and so we have the same number of electrons in our molecule. Now that we have our molecular orbital diagram, we can go back to the actual question. Some students stopped here and were like, I made the molecular orbital diagram, I'm done. But we need to remember that the question is asking us why the configuration we drew makes sense because of the unpaired electrons. So if we go back to our molecular orbital diagram, we see that because the pi 2p have 2 degenerate orbitals, we can have unpaired electrons. If we think about the sigma being below, we would have paired up those electrons and therefore gotten 0 unpaired electrons, and it would not be paramagnetic. So let's just try that out. I'm going to move over here, and we're going to draw just the molecular orbitals, since we already did the full process of making them from the atomic. So this is the sigma to s, sigma star to s. And now we're just looking at what if the sigma 2p was lower in energy than the pi 2p. And again, we would fill up our orbitals. And we see that because this lowest occupied molecular orbital is singularly degenerate, we pair up our electrons, and so if this were the case, boron would not be paramagnetic. However, because it is paramagnetic, we know that the pi 2p is lower in energy than the sigma 2p. So that's what this question was asking. And if you said all of those things, great job, and you answered the question correctly. Now we're going to move on to part B, and it's very related to part A. So we're going to use the same diagrams here. So it asks, is the gas molecule B2 2- more or less stable than the gas molecule B2? Explain. So here he's asking about the boron dimer that has a -2 charge. That is, it has 2 extra electrons. So we're still talking about boron, and thus the atomic orbitals that we're combining are exactly the same. I'll write that down. So we still have the 2s and the 2p from each of the boron. That's not the same energy level. And they still make the same molecular orbitals. But we have 2 extra electrons. So when we go to fill up our molecular orbitals, we now have 8 instead of 6. So not only is the boron 2- no longer paramagnetic because we don't have unpaired electrons, but we also have a difference in the bond order. So if you don't remember what bonding order is, it is when, I'll just put it here. It's how we determine the strength of the interaction between the 2 atoms. And because he's asking, is the boron 2- more or less stable, we want to figure out the strength of the interaction, and that will tell us which is more stable. So the bond order is the bonding electrons minus the anti-bonding divided by 2. Sorry, that's a little messy, but I hope you get the idea. So for boron 2-, which we're talking about over here, the bonding order, we have 2, 4, 6 bonding electrons in bonding orbitals, and we have 2 in anti-bonding orbitals. Divide it by 2, and that gives us a bonding order of 2. So that's equivalent to saying there's a double bond between the boron 2-, the 2 borons in that molecule. So let's move back to our diagram for the neutral boron dimer, and we have we have 2, 3, 4 bonding and 2 anti-bonding. And so that equals 1. So in the neutral dimer, we have a bonding order of 1. And in the charged 2- dimer, we have a bonding order of 2. From this, we can see that the 2- has more bonding interaction, and so it will be more stable. So again, you can't just put that it's more stable. We need to have an explanation for why, and this is a way to explain that.